Hi, everyone, and welcome to my talk, Can We Adapt Experimental Data-Centric AI Principles for Production ML Systems? I'm Bernice Herman. I'm a data scientist, a senior data scientist at WiLabs, and really excited to talk to you about kind of the differences between data-centric AI for experimental side of machine learning and the production side of machine learning. All right. So these are the topics that we're going to discuss today in our session. So I'll give a brief introduction to myself and kind of the perspective that I bring to these issues. We'll talk a little bit about experimental versus production machine learning and how a data scientist may have skills in one and not the other. And then the bulk of the presentation will be focused on data-centric AI principles. So data-centric principles aren't necessarily, things that have been 100% accepted in the community, but they're ideas that seem to resonate with the community of data-centric AI and themes that I see that are reoccurring. So there's 6 principles that we'll go over today and talk about what this looks like for experimental machine learning versus production machine learning. And finally, we'll bring this all together, do a bit of summary, and then provide next steps and contact information for continuing the discussion with me. All right, so a little bit about myself. I am a senior data scientist at WiLabs, and WiLabs is an AI observability and monitoring company that takes a unique technical approach to doing monitoring for machine learning systems. And so we designed a platform to mimic APM observability systems. So think Datadog, Honeycomb, et cetera, that combine this approach, this APM approach, with data monitoring. So specifics that work for machine learning data and data in general. And our solution consists of 2 parts. So an AI telemetry component, which implements a standard for collecting data and logging machine learning data, as well as data in general. And then a proprietary platform for storing that telemetry data, detecting anomalies in that data, and powering the debugging process. My role specifically is really focused in these 2 areas. So other than giving talks like this, which I really love and enjoy, and sometimes writing papers and research and content, I work on the AI telemetry aspect of this. This is our open source library called WiLogs on the left. And WiLogs does something really interesting. It collects aggregate statistics that are important to understanding your data. And this happens even at scale, even if you have terabytes, petabytes of data. Really one of the only ways that you can look at this data that may be massive is to start aggregating it and collecting statistics. And we do this in a pretty complex way. We use data sketches, which are a number of algorithms, probabilistic algorithms, to summarize data in a very kind of efficient, small package, while still giving you the robustness and error bounds and the accuracy that you need for a task like monitoring. The other side of my kind of technical role is on the side of the platform, on the observability platform. And there we run machine learning algorithms and other anomaly detection algorithms on your profile. So WiLogs, when it does this AI telemetry, what comes out is what we call a profile of your data. And this can be for streaming data, this can be for batch data, but this profile and many profiles that you may collect, maybe every 5 minutes, maybe every day, maybe for a flexible amount of time, just to include your training data or something like this. These get sent up to our platform. And there we run a number of anomaly detection and time series analysis models on this data. So I also work on those models and informing the engineering team from that perspective. All right. So this role at WiLabs is really complemented with my role at the University of Washington. So I am a research scientist there. I conduct research in a number of areas, things really related to the things that I do at WiLabs. So evaluation metrics for machine learning. I like to think about meta-analysis of kind of machine learning in general using empirical data. So lots of tests, test sets and benchmarking, this sort of stuff, robustness of machine learning models, synthetic and augmented data. And then another interest of mine is very much structured data versus unstructured data. So a lot of machine learning is focused on images and text. And I think there's really great things there. But how do we compare and contrast that to tabular data or graph data? In that role at the University of Washington, I also teach a software engineering class to upcoming data scientists. So in the professional masters for data science. And finally, I should note that as an employee of both organizations, my presentation here is given from the perspective of WiLabs and not officially as a representative of the university, just legal stuff to get out of the way. The reason that I bring this up is that I think having both perspectives really informs me kind of the issues that we see from different ways of looking at machine learning, as well as another view into how the data-centric AI community is growing. Because data-centric AI, in addition to something that's been adopted by a number of companies and industry data scientists, is also something that has kind of permeated academia and is discussed in academia. And I think this shapes the conversation that we have around data-centric AI, and something to be aware of in our roles as kind of more production of machine learning and data scientists and machine learning engineers. And so I want to bring that perspective as well. All right, so let's switch over to this kind of question that will frame the rest of the presentation. What is experimental machine learning and what is production machine learning, and how do they differ? Okay, I'm sure everyone who is at this talk has seen this graphic at least once. This is from Dee Scully's Hidden Technical Debt in Machine Learning Systems paper. And it is representative of a problem that we all think about when we think about production machine learning. And that is that the software that we write for a machine learning model, this little black box in here, is a tiny aspect of the larger machine learning system that it's contained in. So we have, data collection, feature extraction, kind of infrastructure for serving our models, monitoring, all of these large components that make up the system as a whole. This is maybe a simplified pipeline, well, certainly a simplified pipeline that I created, largely limited to my graphic design ability. But these are a number of tasks that we have when we, at a company or in academia, if we're going to productionize the model, which happens in some cases, but not very many, for creating a machine learning model. And there are definitely feedback loops in between these that I don't include here, also due to my graphic design ability. So we have things like planning and design, acquiring a data set, cleaning and improving your data set, training your model and debugging that model for any errors, and then evaluating on a test data set. This is kind of the quintessential data science pipeline that we think about for machine learning. And I would say that all of these tasks are only one small part of our roles as kind of production machine learning specialists. And I would say all of these things on the left side are the experimental machine learning aspect. So you may do this multiple times, but you get to a point where you've evaluated your model on a test data set, and we can run this manually. The other side is the deployed or post-production machine learning part of the pipeline. And this includes deploying the model and all the infrastructure to have it running and available and reliable. This includes handling data drift. So once we've put a model in production, we don't have a ton of control necessarily over the queries that come to the model. And just with change in environment, change in time, the data that you'll see in the future will look different from the data that you saw when you were training your model. So handling that data drift is kind of part of this production side. Logging and retention of your data. So the data that we have in production is often massive in scale because it's accumulating day after day. And so thinking about data logging and what data to retain is part of this side of the machine learning pipeline as well. Systemic debugging. So I have debugging on the left side, but systemic debugging is really kind of root causing issues that may come from anywhere in your pipeline. So you may have, for example, a stakeholder in your company, a business stakeholder who asks, why are the predictions for the segment of products that I work on this way? And now we're not only just debugging, does this model work, but we're digging into, where in this massive system have issues gone wrong? I mean, sometimes this is definitely in the model. Continuous evaluation. So as someone who does research and evaluation metrics, I could talk about this all day, but I'll just say that evaluation post-production compared to pre-production looks different. And the task of kind of running evaluation over time with this time aspect and with the many other complications that come with production is a task on the post-production side. And then finally, model feedback. So tools to perhaps retrain your model or take insights from monitoring of this model to affect the business. These are all what I'm categorizing as model feedback. So this chart is important because we are going to kind of reference this difference between experimental and production machine learning for each of the DCAI principles that we talk about. All right. And so I just want to note that the skills that go into production machine learning kind of are well beyond those needed for building models and experimentation. Of course, there's very specific skills that you need for building models and experimenting and being kind of state of the art in that side. But this is one example. This is made with ML by Goku, who is also presenting at the summit today or tomorrow or yesterday, depending on what day this is scheduled for. But this is one really great resource for kind of digging into ML ops and the production side of machine learning. And you can contrast the sorts of topics that you see on the right, things like packaging, organization, logging, versioning and Docker, continuous integration and delivery, monitoring, system design, with the sorts of things that I tend to see in a kind of traditional machine learning education, things related to machine learning models, different types of regression, different types of deep learning models, and so forth. And we see something very similar for another resource that I wanted to plug. And this is ml-ops.org. And this is just another example of resources and the number of skills that you have to consider on the production machine learning side and the ML ops side of things. And really serves to highlight that these two things are different. And we certainly have to have knowledge of both to be kind of effective machine learning engineers and data scientists. But we know that there's a body of skills, a body of practices that we will consider differently than those of just machine learning model training. Okay. And then just the last thing to note here, which I find really interesting, is even kind of tools and communities meant for model training and very much at the experimental phase of machine learning often run into some of the aspects of production machine learning data that we'll talk about in a little bit. So for example, in Kaggle, at the time of counting these, which was last year for me, there were 14 of 40 of the most voted Kaggle data sets. So just starting from the top, based off of the most votes, that included some sort of date or time index column. So things like with credit card fraud detection or the COVID data set, what was the date that this example was recorded? And interestingly enough, often for the way that we conceptualize experimental machine learning, we just completely get rid of that date information. We kind of throw all of these examples in one large pile and use that to go forward. That is very different from how we think about production machine learning. All right, so let's move on to the data-centric AI principles. This is the remainder of our session here. And so for each principle, what I'm going to do is name the principle, as you'll see here, and then have on the left side the experimental machine learning kind of advice with that, and whether or not experimental machine learning side kind of agrees with this and some suggestions. And then the same for the production machine learning side. So in some cases, production machine learning it also kind of matches this principle, maybe with some differences in how you implement it. And in other cases, the principle is kind of contradicts how we ideally would conduct production machine learning in a data-centric way. Okay, so our first principle, one both sides can get behind, is understand your data set and its generating processes. So a lot of advice, a lot of discussion around data-centric AI is around this concept of just really focusing and understanding your data set and where that data comes from. So discussion about, from the papers that I've read and kind of dug into, discussion about understanding which features and the feature engineering that might be involved. There's quite a bit of discussion about label categorization. So, for example, in ImageNet, the 1,000 labels that you have, how are those labels distributed? You know, how many of those are dogs? Very many dog breeds. How many are labels that are in some way hierarchical? Another important thing to discuss and understand and continue to grapple with, although it's very difficult to solve, is the data set source, particularly for experimental machine learning scenarios where you likely are scraping data from the internet. Other things to consider are missing data and the ethical impacts of your data. So some suggestions that I have when thinking about the experimental side is conducting exploratory data analysis. So things like plotting the scatter plots for various features, looking at the means and the distributions and these sorts of things for all of your features. And there's some great tools, including what we provide at YLogs for profiling your data set. The other that I mentioned briefly before is take care with scraped internet data. So many data sets are, large data sets that are scraped from the internet for some different purpose. And so you really have to be careful about the distribution of that data set relative to the distribution of data that you will see in your task. Inspect for any hierarchy in your label set. So again, the example for ImageNet. ImageNet is built off of, I believe, WordNet, and WordNet is hierarchical. So it has things like dog, and inside of the dog category, it has different breeds of dogs. But for ImageNet, a selection of 1,000 labels were kind of picked. And they don't respect that hierarchy necessarily. So there may be some categories where there are multiple labels that are true. And these sorts of issues, and in understanding these sorts of issues, and then later we'll talk about fixing these sorts of issues in your data set, is a large part of what people are discussing when they're talking about data-centric AI. And then finally, I'll say data sets for data sheets or similar tools are structures for information gathering about your data set. So being able to write down all of this information that you find about biases and distributions of your data can be really helpful. All right. Before we get to the production machine learning side, I guess I want to note, which I didn't make clear before, is that when we as data scientists and machine learning engineers and other professionals who are working in the industry with machine learning data, we're not just solely doing the production machine learning side of things. We're often doing both. So experimental machine learning is a task that is done at every company that productionizes a machine learning model, right? They have data scientists that do this exploration of the data, that train a model, all of this work. This is in addition to the production side. So it's not that you are choosing one or the other. It's often that if you're doing production machine learning, you're doing both. And if and maybe in an academic setting or some other settings, you may be solely on the experimental side. Okay, so now production machine learning for our first principle of understanding your data set and its generating process. So this is definitely true, but there are additional focus areas. So in addition to all of the things on the left, you must also think about the system that contains the model. And again, as we saw in that D. Scully picture, like machine learning code is a very small aspect of your system. And often when we're thinking of our data set on the production side, we're thinking of outputs from that system as a whole. The other things to know are things like time series. So this data is collected over time. And so we need to consider that. And then the frequency of data. So is this streaming data? Is this batch data? If they're in batches, how often does it come in? And then metadata. So there's often, lots of information about the system, the world at the time of these predictions. And this is really important data to include in our production machine learning data sets. But then also something to deeply understand and understand the generating process so we can understand how errors might arise. So some suggestions is to include relevant metadata about your system. So for example, dates of system failures. If you have an outage in, let's say, some remote part of your system that would affect the queries that come to your machine learning model, that metadata should be included inside of your production machine learning data set somewhere. So when we include this sort of information in our data set, we can start to understand why there might be shifts in the kind of distribution of queries that you get, or sort of things like this. And this also is true for the environment as a whole. So things like if you're a retailer, things that are really important to you may be things like holidays and weekends. And this is not something we typically consider in experimental machine learning. I'll talk a little bit about why, but this is something that is really important, I think, in general, but certainly for production machine learning data sets. Another thing I suggest is to note how users and software system constrains the model queries and data. So if you have let's say you offer to the internet or your customers a API to use your machine learning model. Let's say it's like facial recognition. So if you offer a facial recognition on an API and anyone can come to the website and upload a picture to conduct this facial recognition, there are still some constraints, right? So who are the customers that are likely to see this surface? What is the process? What sorts of images do you accept? What sorts of expectations do you set in the kind of the verbiage of the webpage that describes the system? All of these things can constrain the sorts of queries that your model will see and the distribution of queries that you'll see. In more constrained scenarios, you may have a system that makes queries based off of some internal process, right? This is much more constrained, but this is worth noting in your production machine learning data, or at least in understanding your data set and how it may be changing when any of these kind of constraints change. And then finally, consider how your time series data is aggregated. So if we are continually running a production model, you may decide to batch your data. So for example, there are some systems where you are running some process, let's say it's like a recommendation for an email, like an email you send to your customers weekly. So you run these recommendations weekly or maybe a couple times a week to aggregate and send this email campaign. This aggregation is very different from a system that is fully streaming and that in real time, like customers make their own individual queries about recommendations for a new product. Knowing how we aggregate this information is really important to understand if there are any trends or artifacts that could be obscured. So for example, it could be that your system, for whatever reason, makes different predictions based off of, let's say, the latest products that are sold. And the products that are sold vary across the weekend and the weekday. So if you run a weekly process to send emails and predictions, and you collect your production machine learning based on that weekly process, you've now obscured kind of this artifact of your model that is related to the day of the week. And so we want to be careful about this. It's not to say that that's wrong, but this is something you should consider in understanding your data set. Okay, so I have an example here for our experimental machine learning data sets. And this is IRIS classification data set, very popular one. And so these left 5 most columns represent what we typically think of for an experimental machine learning data set. And that is the features and the ground truth or target, as I've written here. In the next slide, you see things that we're more likely to see for a production machine learning data set. In addition to many of the things that I just discussed that are not included in here, you'll see these left forward features. You likely won't have a target in a production data set. So let's say this is an app now that people send a picture of a flower that they've taken with these different lengths that are calculated. We don't have the target or the true ground truth. What we do have is a model prediction, and we likely have some other information such as like a confidence score or this sort of thing. This is the difference. So this difference between orange and blue is a difference that you'll often see between the production and the experimental data sets. And this lack of ground truth will become really important later. Okay, so the next thing to consider is, again, this time aspect that I mentioned. So on the left, we see what looks like a typical experimental data set setup, where we have a static training data set that was collected over some unknown amount of time, or from some website, or from some existing machine learning data set. And we split that static training data set into a training split, a validation split at times. So this is to help find hyperparameters and do fine tuning of the hyperparameters of your model. And then finally, a test data set, which we'll be using to evaluate accuracy in a number of evaluation metrics. This looks quite different from what we'll see for our production data set on the right side. So there, we are collecting data, again, over time. It may be streaming, it may be daily, as it is in this graphic, where we're collecting our training data. And then often it's solely the training data each day. In a rare number of cases, and we'll talk about those in a bit, we may have some sort of ground truth, which I'm representing with this darker blue at the bottom. And then this also often comes in a delay. All right, let's move on to our second data-centric AI principle. And this is that information flows from your data set to your machine learning model. This is one of the reasons that the quality of your data set is so important and why we talk about it so often in data-centric AI, because in experimental machine learning, we use that data set to train a model. So what it means is that the information contained in that data set is going to directly affect the model, the accuracy of the model. And this, without this principle, the kind of emphasis and need for data quality is quite different. So some suggestions on the experimental machine learning side, where information does truly flow from data set to model, is to consider, again, how you may have additional information that impacts your model training, even if that information was not information that's going to be in the model itself. So for example, you may consider training models using some segment of the data, some information about a customer or things like this, just to understand better the model that you're training, maybe the robustness of the model, and so on and so forth. Okay, let's move forward to production machine learning. This is our first example where I would say this isn't quite true. So this principle that we have for data-centric AI does not really match what we see in production, because for production data, your data does get fed sometimes back to model development with kind of model retraining using the new data that you have. But production machine learning data sets often are about the flow from your model and system to your data set, to analysis. I mean, this is what allows us to monitor and debug our system. So our suggestions for this is to collect as much data as you can about your system. This is really important. And that even kind of simple analysis and monitoring of this system can be informative, or of this data can be informative of your system's health. So one thing I wanted to note here is just, again, that you can decide to kind of collect data in many, many places during your machine learning process. And because machine learning production machine learning data sets are really about information about the system and exhaust of the system, this can be really helpful. So collecting telemetry right as you're acquiring the data set, kind of between all of the steps of transformation and cleaning of the data set, during training, during evaluation, with respect to kind of data drift and corrections of data drift. You can use this data as logging. This is what YLogs, our open source product, is intended for, as well as debugging, and certainly for evaluation and model feedback. And this extends beyond just the larger system and also into the internals of your model. So there is a little less research on exactly how to translate differences in distribution between, let's say, different layers of a deep learning algorithm, which we see here, between each other, kind of directly into actionable information. But this is something that has kind of the beginning of research for and can be informative. So you can imagine even going as far as collecting information after certain layers inside of your model, if it's fast and quick and easy to collect. All right. So let's go into the third DCAI principle, and that is that prioritizing data set quality can bring more success than machine learning model architecture improvements. So this insight is really kind of the fundamental pitch of data-centric AI. Um, and so this is something that Andrew Ng speaks about. This is something that other researchers have started to look into. But there is growing evidence, certainly not conclusive, but growing evidence that the data set on which a machine learning model is trained proves more important than the model architecture. And we'll look into some examples of this. But so some suggestions that I have is to compare the model performance across each step of your data cleaning and transformation process, and see how kind of iteratively these changes in data set quality can impact your evaluation metrics at the end of the model. Another suggestion that I have, and we'll point to a little bit right after this, is to look into work on this empirical kind of meta-analysis of machine learning, especially with respect to robustness, which is really important for production systems. There's lots of research that's kind of sprouting. I'm really fond of the research by Ludwig Schmidt, a colleague of mine at the University of Washington. All right, so for production systems, this is also true. Improving dataset quality can bring a lot more success than machine learning model architecture improvements. And in addition to just kind of the accuracy and robustness of your model, it can also inform debugging, explanation procedures, and the processes of building and keeping a model healthy and stable. All right, so this is one chart that Andrew Ng presented in his chat on kind of MLOps from model-centric to data-centric AI. I believe one of the first presentations he gave kind of introducing this data-centric AI concept. And you can see here kind of for a number of models that the data-centric approach improved accuracy more so than the model-centric approach. So iterating on the model architecture and making more complex models. The interesting work that I want to show here and do a little bit of an explanation is the work from the lab of Ludwig Schmidt. So this is from a paper that starts accuracy on the line. And what this shows is a couple of things. So if you see on the x-axis here, what we see is ImageNet accuracy. So ImageNet for computer vision, it's a very popular data set of images. And there has been a lot of effort recently to create replications or slight alterations of the ImageNet data set that represents a sort of alteration that we feel that models should be robust to. So this is one particular ImageNet alteration here called ImageNet vid anchors. And what we're showing on this plot, so that's on the y-axis. So what we're showing in this plot is how well do many, many, many models, each of these dots on the plot are a different trained machine learning model. How well does the accuracy on the kind of altered data set, the ImageNet vid anchors, compare to the original accuracy on ImageNet? And what we would like to see is that the accuracy on ImageNet is just as high as the accuracy on this augmented version of ImageNet. That would be on this dashed line. That is, of course, not the case. We know that when we change the distribution of data, when we go outside of the original distribution we've trained on, that our models get less accurate. And the question now is like, how less accurate? And are there any trends here? And so something really interesting that you'll see in a lot of cases, though not all, is that many of these models fit really well onto a line. It's not this perfect line of accuracy being the same across the tube, but it shows that no matter kind of how low the accuracy is originally, so you'll see here on the left, the purple is like nearest neighbor, so very, very simple algorithm. It has fairly low accuracy on ImageNet, so a little bit over 10%. It has a little under 10% on this augmented data set. if you scale across different complexities of models, you see, so going up here to the blue section, low accuracy convolutional neural networks, and going up to more advanced, so neural networks up here, you see that many of them fit this line. So the accuracy on ImageNet is increased, and the accuracy on the augmented ImageNet is also increased, though not equally. This tells us something really interesting, and that is that no matter what model architecture we use, they roughly fit the same line. And this is really amazing, actually, and not something even the authors expected when creating this. And you'll see just a couple of examples of of models that are built on more data in the green that kind of break out of this line. Similar to a couple of examples with models that have some direct robustness intervention. So this is some research kind of approach that they took to be able to make the models more robust. And you'll see that a couple of these break the line as well. So the amazing thing is really in the next paper that we look at here, also from the same group, although a different first author, that changes in the training set is what makes an effective change in robustness. So what they're looking at here is CLIP. And CLIP is a recent model that is incredibly powerful and surprisingly robust. And the question that the authors had is, why is CLIP, this kind of image and text combination model, a multimodal model, more robust? And there are a couple of theories that they explore in this paper, but the one that shows any potential is that it's actually the data set itself. So what you see here on the left is the gray line is the number of models. So again, the dots are models that are trained on ImageNet, so the data set that we refer to. The green line are a number of models that are trained on the data set that's used for CLIP. And so you see that the place that we see this actual jump in robustness is actually with a change in data set, with a kind of a better data set for this task. And I find this incredibly interesting and a strong argument for data being the important aspect of model success and accuracy, not the architecture, because the architectures, models of different architectures fit on the same line. Okay. Thank you for sludging through the research for me. I find this super interesting and happy to discuss more. Okay. On to the fourth principle, and this is to iterate on and continually improve your data set quality. This is absolutely true, and a kind of defining principle of data-centric AI for experimental machine learning. Lots of what we'll talk about, I'm sure, with others are tools to be able to iterate on the labels of large amounts of data, and to explore data cleaning and do this transformation much more easily. For production machine learning, the same is true. You still want to continue to iterate and continually improve the data set quality, but there is one caution that I think is very important, and that is that for production machine learning data sets, there are two purposes of your data set. So both we want to inform future model training. We want to build up a data set that we can train models on in the future using kind of production data that we've experienced. But we also want to keep a record of your production system, right? So changing and iterating on your data set should not come to the expense of understanding how your data set or how your model operated last month. We want to be able to do both. And additionally, there are different things that we consider improving. So less focus perhaps on label quality and more focus for production data on things like the metadata, the environmental information, correcting bugs and logging and reporting. And so just my suggestion is to take a lot of care for keeping accurate records, historical records for this debugging. I have an example when I worked at Amazon, where we had a downstream system that provided to us forecasts of each of the products that we sold out of our warehouses. My team is was charged for determining how much we should buy and store inside of our warehouses. So the forecasts of the sales for those products was very important. Well, the forecasting team at one point, when they improved their algorithms for forecasting sales, would go in and replace the forecasts that they made in the past in the same database, without a lot of information about when those have been changed and which records have been changed. And this caused a large issue, right? Like this is kind of a clear example of this conflict of goals. Because when we wanted to debug our system, let's say a couple weeks after we make a prediction, we get a vendor manager who comes and says, hey, you predicted that we should buy 2,000 extra of this type of shoe than we expected that you would buy. Why did you do that? We want to go back and look at the information that we have, our data set, our production and machine learning data set, and say, okay, well, what were the inputs to our model? What was the information that we had when we made that prediction last week? And this is really this conflict between, are we storing a record of our production system, or are we trying to iterate and improve on these forecasts, even if they're forecasts for forecasts made in the past, maybe for the future. Okay, I'm going to move on for time. So now we are down to our last two data-centric AI principles. One is number 5 is consider removing examples from your data set if they cannot be fixed. And this is a step beyond the one that we saw just before of continually improving your data set. And so in DCAI for experimental machine learning, there's been suggestions that if an example inside of your data set is low enough quality, you can't fix the label, it's just not a good quality example, perhaps you should remove it from your data set altogether. And this does a couple of things for us. It reduces variance in our data. It reduces the Bayes error, the potential the low bar for the potential amount of error we can have for our model. And it makes some sense in the case of training a model. And so it makes sense that this is a principle that is considered in the data-centric AI community. There's certain things that I would suggest to you when you're doing this. So you should consider any patterns and biases in the examples that you decide to remove. You should search the data set for nearest neighbors using different metrics, not just Euclidean distance, to confirm that similar examples are still in the data set when you remove others. You can also consider the data difficulty of each example. So this concept of some examples inherently are very easy, and across many model architectures, you're likely to predict correctly on this example all of the time. There are some examples that are just inherently difficult. So it is unlikely that you're going to predict very well on even some of the best models that we have, the most state-of-the-art models. And then there are some examples that are in the middle. And some would suggest that those examples that are in the middle of the difficulty spectrum, those are the ones that you really want to retain and refine and emphasize in your data set. And you want to de-emphasize the ones that are either ridiculously easy, maybe you undersample those, or those that are ridiculously difficult. All right, but let's move on to production machine learning. So my suggestion for production machine learning is no, you don't want to remove examples from your data set for the same reason that I just explained, that there's sort of two roles for your production machine learning data. One is as a record of your system, and the other is to inform future models. And so you want to separate, perhaps you want to separate a data set that you're starting to collect for new retrainings of your models, but that should be very separate from what we traditionally think of as your production machine learning data set. We addressed this in our paper last year at the DCAI workshop at NeRPS, and we called it data vast and low in variance, kind of contrasting the data that comes quickly that we think about recording and the data that's slow and low in variance, this clean, pristine data set that we may want to train our model on. So feel free to look into that paper and happy to discuss it more after the presentation. Okay, finally, our sixth principle. So this is that label quality is the primary focus, not the data distribution when we think about data set quality. So this is certainly not something that someone has expressed very explicitly, but just reading the literature and the discussions about data-centric AI, this is the way that people tend to focus is on label quality. And this makes a lot of sense. So supervised learning, where we use these labels in training the model, is by far the most common sort of machine learning that people are doing. And there's a lot of poor label quality out there. There's an interesting study that shows as much as 3.4% of labels across several data sets in the study, including ImageNet, are present. And so things that we consider are things that I've mentioned before. So things like, how are labels categorized? Are there some hierarchy that isn't there? Things like balance of the labels. So if you have 1,000 labels, are there some labels that are overrepresented in our data set? Does this affect our model? And there are techniques to consider about recording label subjectivity and uncertainty. So you can not only have a label, but you might have a label with some sort of score that represents how certain you are about this label. This can be really helpful. But for production data, while both are interesting, both label quality and data distribution, I would argue that data distribution is more important than label quality for production data. And this is because in real environments, we have to think about things like data set drift. So data set drift, especially in systems kind of over time. And further, ground truth labels are expensive, and you're unlikely to have ground truth labels in a production system. In the next slide, we'll go over some examples about systems where you may or may not have ground truth labels, but it's just really infeasible to center production machine learning data sets and then the discussions around data-centric AI around labels if there's something that are unlikely to be present in a lot of production systems, or at least initially. So some suggestions are to consider different sorts of drift. So covariate shift. So this is the shift in kind of the inputs. Prior probability shift. This is kind of shift in the outputs that you expect. So the Ys. But then also considering for some examples and some applications, concept drift. This is a shift in what inputs will lead to a certain label. So it may be that in a changing environment, we look at an image and in the past we would label it in one way, but now we would look at that very same image and label it in a different way. This is a really complex type of drift or shift. This is not something that is talked about as often as the other shifts. But it is something that we can run into for production machine learning, and definitely something that you should consider for your task at hand. Okay, so these are some examples here of delayed and manual ground truth collection. So as I mentioned in the slide before, there are just a handful of cases where we may have ground truth kind of with certainty. And even in those cases, it's often delayed. So the example of sales or demand forecasting, where I'm predicting how many people may buy a product if I'm a research or a retailer, that we will eventually get a ground truth for. We will get the answer. So if I predict how many people buy a certain product next week, in 2 weeks from now, I will have the answer of how many people bought a product during that week. Similar for customer churn prediction. This can often be even a longer delay because you may make a prediction that this particular customer with these attributes and features, they are likely to stay on the platform in the next 6 months or the next 12 months. We have to wait 6 months or 12 months to determine whether or not they did indeed stay on the platform. But it is a case where we do get automated ground truth. We just kind of naturally get ground truth. That's actually much more rare compared to the case where you're not going to naturally get ground truth. You'd have to actually kind of go through the expensive effort of getting someone to label this data or finding proxies for your ground truth. So for example, image captioning. Depending on the application, there are more applications that maybe combine both and uniquely come up with both text and an image. But in many applications, if you get users giving you multiple images, no one's going to give you a caption unless you go to Mechanical Turk or you somehow get those labeled. Same for classification of images, either for medical or other situations. Same for things like speech recognition and content moderation. Okay, and now on to wrap up here. So then the next thing I'll say, just point out to you, for those of you who are really thinking about how to evaluate your models with this sort of delayed ground truth, there's a really interesting blog post and kind of set of research articles on delayed progressive validation. So how do you evaluate your model with delayed ground truth labels? I'll point you there. Okay, so to wrap everything up, we talked about production versus experimental machine learning, and we went through 6 different data-centric AI principles that are largely discussed with respect of experimental machine learning, but I really want to bring into the conversation of production machine learning and how suggestions for how to implement these principles or even kind of conflicts with these principles arise for production systems. And then next I will just do a quick explanation again of why I work on the things that I work on and why I think it's so related to data-centric AI for production models. So again, when we, so one practice that we have for production systems is to collect data to not only inform our models that we're training, but also to understand our system. And there's many tools that software engineers have for understanding their system and how it has operated. And logging is one of those tools. But logging data requires certain kind of purpose-built solutions and techniques to be able to do this efficiently, to be able to kind of gain the insight that you want from your logs. And so this is why I work on YLogs. It really allows me to think kind of a lot about how do we collect data about not only experimental machine learning data sets, but production machine learning data sets where we focus. And we do this in a way using data sketches that allows us to merge this data set together and really works well for dynamic data or streaming data even. Okay. And again, when you have something lightweight that allows you to log data and allows you to analyze data that's purpose-built for production data, it really enables you to start building your production data set to include as much information about your system as you can, because all of this information is informative to you and helps you to better understand your system's health. And so I suggest kind of collecting data for your production machine learning data sets from many, many places across your machine learning pipeline, and using your experiences in doing that to really build on kind of what data-centric AI means for production systems. And together, I think we can continue to have discussion. We're all here probably at the forefront of data-centric AI that's tailored for production systems and building tools and practices to be able to do so. And with that, I want to thank you for joining my session. I'm really excited about these topics. I have so much more material that I could have gone onto. Obviously, lots of stuff that we already went into. I would love to continue to chat with folks about these topics and to continue to discuss kind of how data-centric AI evolves for production systems as well as for experimental systems. Because again, we also run the experimental side of the pipeline as well. So please feel free to reach out at any of these addresses or social media things. And please do check out YLogs. It's open source, it's on GitHub, and feel free to join the Slack as well. Thank you.